Welcome back. Today we are diving into an important concept in linear algebra, linear dependence and independence. Imagine you have a set of vectors and you want to check whether all the vectors are unique or not. That is, you want to check whether all the vectors are original or not. Is there any copycat vector which are present in the set? For that, you have to check whether any vector is a linear combination of others or not. And in this checking process, linear dependence and independence is going to help us. So let's understand that with an example. Here I am taking two vectors from R2 and naming those vectors as alpha and beta. I can easily see that the vectors alpha and beta are not unique because alpha I can write down in terms of beta, which is this one, and also beta I can write down in terms of alpha. So 12. For these two vectors, I can easily see that they are not unique. Now I'm taking one more example. 1, 0 and 0, 1. Now if we can see that these two vectors are not dependent on each other and they are unique vector because this 0 I cannot make it as a number, especially 1, and also this 0 I cannot make it a number 1, 2, 3 or something. So these two vectors are not dependent vector, they are independent vector. Now take one more example. Let us take now for this set also you can see that the third vector I can write down easily in terms of the first two vectors. And therefore this set is also not linearly independent set. For this set of vectors we can easily see and tell whether these set of vectors are independent or dependent vector. But for a larger set of vector and for the vectors which are from R3, R4 or from Rn, for that we cannot just see and tell whether the vectors are linearly dependent or independent. So for that we need mathematical formulas. So let's just learn the definition of linear dependence and independence. A finite set of vector alpha 1, alpha 2, alpha n is said to be linearly dependent if we can get scalars C1, C2 and Cn where the scalars are not all 0 such that the linear combination of the vectors alpha 1, alpha 2 and alpha n, that is C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is equal to 0 vector. Then this set is called as linearly dependent set if this linear combination becomes 0 vector whereas all the scalars C1, C2, Cn are 0, then the set of vectors alpha 1, alpha 2, alpha n is said to be linearly independent set of vectors. Now we'll check this mathematical definition to the earlier vectors we have considered. For the first example, we can see that if we just write down minus 2 into alpha, that is the first vector, plus 1 into beta, then this combination becomes 0 vector. So we are getting a non-zero scalar minus 2 and 1 for which the combination becomes 0 vector and therefore the vectors alpha and beta are linearly dependent vector. For the second example, 1, 0 and 0, 1. So again, take the combination C1 into the first vector plus C2 into the second vector is equal to 0, 0. If we can find out a non-zero C1 and C2 for which the combination becomes 0 vector, then we'll say these vectors are linearly dependent vector. Now let's just find out. So this becomes C1, C2 is equal to 0, 0. From here we can get C1 equal to 0 and C2 equal to 0. So we are not finding any non-zero C1, C2 for which the combination becomes 0 vector. Therefore, these two vectors are linearly independent vector. Now for the third example, easily we can just write down -1 into the first vector plus -1 into the second vector plus the third vector. Now if we just calculate, it will be -1, -2, so -3 plus 3, which is 0, then -2, -1, -3, then +3, again 0. So for the non-zero scalar -1, -1 and 2, this combination becomes 0 vector. Therefore, these vectors are linearly dependent vector. From these examples, we have some more observations, which are we have considered a linearly dependent set. Now, if I add any vectors in this set, suppose I have added 0, 1, 0. Then always actually we can get this combination as 0 vector. So we are getting non-zero scalar -2 and 1 for which this combination becomes 0 vector. If we add more vectors also in this set, then also we can write down this combination again, that 0 into that vector plus 0 into one more vector, and in this way we can continue. So we can see that in a linearly dependent set, if we add many number of vectors, that does not change the linear dependence of that set. So any superset of a linearly dependent set will always be linearly dependent. Let's check this for the linear independent set. We already have checked this set is linearly independent set. Now I am taking a subset from this set. Suppose this vector. Now this set will always be linearly independent set because this combination will be 0 vector if and only if I multiply 0 with this vector. Otherwise, for any non-zero vector, we cannot make this one as 0 vector. So, from this we can get any subset of a linearly independent set will always be linearly independent. From here we have one more observation, that is, if we take any singleton non-zero set, then that will also be linearly independent because this vector I can only make 0 vector by multiplying 0 with this vector. Otherwise, any non-zero scalar cannot make this vector as 0 vector. So, the set of singleton non-zero vector will always be linearly independent. Now let us consider the last example. If we take null vector with any set, then that set will always be linearly dependent set because for the null vector we can always get a non-zero scalar for which the combination will be 0. So with the null vector you can give a non-zero scalar C for which this combination will be 0. So any set containing the null vector will always be linearly dependent. I have written the theorems here which just now I have discussed, which are superset of a linearly dependent set is linearly dependent, then Next theorem, linearly independent subset will always be linearly independent. Then any set of vectors containing the null vector will always be linearly dependent, and this set consisting of the non-zero vector single is linearly independent. Now we solve a problem. The problem says examine if the set of vectors is linearly dependent or not. So basically we have to take the linear combination, make it equal to zero vector, and check whether we can get a non-zero C1, C2, C3 or not. Calculate the left hand side and get the system of homogeneous equations in terms of C1, C2 and C3. Now we already know that C1 equal to 0, C2 equal to 0 and C3 equal to 0 is already a solution, but we need to find out whether there is any non-zero solution of C1, C2, C3 exist or not. For that I will use the solution procedure for homogeneous equation and convert the coefficient matrix to a row reduced echelon form and find out the rank of the matrix. I can see that the rank of the coefficient matrix is 2 and therefore there exists a non-zero C1, C2 for which the combination becomes zero vector, and hence the vector 2, 1, 1, 1, 2, 2 and 1, 1, 1 is linearly dependent vector. One more example which says that examine if the set of vectors, this one, is linearly independent or not. Now for this example, I will apply the matrix procedure. For the larger set of vectors, you can apply the matrix procedure. For that, you have to form a matrix with the help of this vector. So you can write down the vectors row-wise or column-wise, it does not matter. So here, I will write this vector column-wise. So first vector, then second vector, then third vector. Now we'll find out the rank of this matrix. Now, if the rank of this matrix is equal to the number of the vector present here, then we'll say that the set of vector is linearly independent, otherwise it is linearly dependent. Because the rank of the matrix means there are that number of linearly independent vectors. For this one, if the rank of the matrix is 3, that means in this matrix, there are 3 linearly independent vectors are there. So, we'll proceed for finding the rank.
So the rank of the coefficient matrix is 3, which is equal to the number of the vectors given in the set. Rank is 3 means all the vectors are linearly independent, and hence the given set of vectors is linearly independent. Now this problem says we need to determine the value of k for which the set S is linearly dependent. Now again I will follow the matrix procedure and I will form a matrix with the help of these vectors. Now we can see that the set of vector is linearly dependent. That means the rank of this matrix is obviously less than 3. because if the rank was 3, then the set was linearly independent. Now, since the rank is less than 3, obviously the determinant value is 0. क्योंकि अगर डिटर्मिनेंट वैल्यू नॉन जीरो होता तो ये रैंक 3 हो जाता. So we'll use this definition. So make the determinant value is equal to 0 and then solve this. So we can see that k is equal to 2 and minus 1, for which this set is linearly dependent. Now the second problem is same, so I am giving this problem as a homework. Now come to the next problem. The problem says that alpha, beta and gamma are linearly independent set of vectors. We need to prove that this set is linearly independent. So to prove this set is linearly independent, again we will consider the linear combination of these vectors and make it equal to the 0 vector. Now since alpha, beta and gamma is linearly independent set of vectors which is given in the problem, therefore all the coefficient with alpha, beta and gamma has to be equal to 0. So we are getting a homogeneous system of linear equations in terms of C1, C2 and C3. Always remember that here 0, 0, 0 will become a solution, but we need to find out whether there exists a non-zero C1, C2 and C3 or not. So for which we'll follow the solution procedure of homogeneous linear equations. It's very evident that the rank is 3 and therefore we can say that this system has only 0 solution. That is C1 equal to 0, C2 equal to 0 and C3 equal to 0. And hence the given set of vectors is linearly independent, this one. Next problem, we'll check whether these three matrices are linearly independent or not. Again, we'll consider the same. We'll take the combination of these three matrices and make it equal to the 0 matrix, and then we'll check whether we can get any non-zero C1, C2 or C3 or not. Now develop the equations. Now we have 6 homogeneous system of linear equations in terms of C1, C2 and C3. We'll solve this system and get the value of C1, C2, C3. So for that we'll consider the coefficient matrix. Now here, instead of using the row elementary operation, I will use the column operations, and that will give me the easier and quicker solution. The rank of this matrix is equal to 2 because the third column is 0, and which is less than the number of variable, which is 3. Hence, there exists a non-zero C1, C2, C3 for which this combination becomes a zero matrix, and therefore the given matrices are linearly dependent matrix. Now the next type of problem, here two polynomials are been given. We have to check whether these two polynomials are linearly dependent or not. Again, we will take the same procedure. C1 into the first polynomial plus C2 into the second polynomial is equal to the 0 polynomial. Since we are considering polynomial, so here right hand side will be 0 polynomial. Now again, putting the value of u and v, we will get the equations as now we can see that this system of homogeneous equations is nothing but a one equation. So the 2, 3 equations are redundant equations, and we are getting basically one equation, which is this one. So putting C2 equal to some variable k, where k is a real number, we get the solution of C1 as minus 2k. Therefore, this system has infinitely many solutions, and the given polynomials are linearly dependent. We'll take one solution as if we take C1 equal to minus 2 and C2 equal to 1, then we can see that the given polynomials will be linearly dependent. Though for these two polynomial u and v, we can easily see and check that they are linearly dependent. But if any complex polynomial are been given, then this will be the procedure for checking the linearly dependent or independence. Now for this function ft, gt and ht, we have to show that they are linearly independent. Again, we will take the linear combination. Will be equal to the 0 function. Putting the value of ft, gt and ht, we get so this combination will be equal to 0 function for all values of t. Now we are taking first t equal to 0. Let us get one equation, which is So this is a homogeneous system of linear equations. Again, we have to check whether there exists a non-zero solution of C1, C2, C3 or not. So we can see that the rank of the coefficient matrix A is equal to 3, which is equal to the number of variable, and hence this system of linear equation has unique solution, which is C1 equal to 0, C2 equal to 0 and C3 equal to 0. The functions ft, gt and ht are then linearly independent. Here I have solved all kind of problems related to linear dependence and independence and have given some problems for your practice purpose, and you solve and check whether you can solve this problem independently or not. So I thank you for your attention.